or should I do? Okay, good.
Yes,
So,
I started.
Okay, perfect.
Okay,
so
I also started it. Yeah, perfect.
So today we're going to have two sessions dedicated on the interplay between black holes, spacetime singularity, and higher derivatives. And okay, the first speaker of today will be James Booth, and so he's already sharing the screen. So I think you can just start talking whenever you want.
Okay, thank you, Francesco. I have my timer here set to 25. I hope that's correct. So yeah, thank you all for being here today, and it's a great honor to be part of this conference. I've really enjoyed the discussion sessions, and I would specifically like to thank Luca and Sravan for making night today and staying up and organizing this entire conference, and creating this kind of really nice atmosphere for discussions and talks. And I really appreciate it, and it's a lot of fun to be part of it. My name's Jens. I'm a postdoc at the High Energy Theory Group at William and Mary. And today I want to talk about the green function approach in weak field infinite derivative non-local theories. And this is based on work I did during my PhD with Valery Frolov and Andrei Zelnikov in Edmonton, and their master student, Jose, as well as Ivan Kolar, who is Anupam's postdoc in Groningen right now. So this is I think where we are right now. And I think this is interesting. Luca and Sravan were saying the other day they were going to bed at 4 or 5 a.m. and this is when I got up this morning. And I think this is a nice experimental, performance of what non-locality really can mean as well. So I think it's quite fitting. I also want to plug my PhD thesis, which is on the archive right here. Lots of the things that I'll talk about today are in there in much more detail. So if you want to check that out, that's the number. All right, so what's the motivation for today's talk? I want to kind of develop what Andre and Valerie and I jokingly call a non-local intuition. So we want to use the green function approach, and we have used it to study a wide field of non-local weak field problems. So we've studied stationary, static, ultra-relativistic particles, branes in weak field gravity, applied this to Maxwell theory, looked at quantum scattering, particle production on a delta potential in quantum mechanics, vacuum fluctuations, fluctuation dissipation theorem at finite temperature, and even corrections to black hole entropy in 2 dimensions via the Polyakov effective action. And we use these kind of methods in all of these works. So it can be applied to a whole bunch of things. But this conference is also about, or this workshop is also about interaction, right? So I hope to address a couple of the comments and remarks that were raised on Tuesday and Wednesday. Particularly, I wrote down some that I remember. Richard Woodard was asking about the integral kernel. Terry mentioned the Cauchy problem, and Frank mentioned this infinite derivative toy model. And then Irina mentioned heat kernel methods. Philip was asking about correct IR behavior of non-local theories. And Robert was mentioning smearing out as a regularization mechanism. And I'm sorry for anybody that I missed, but I think we will see all of these concepts somewhere in this talk today. So I want to start with non-local green functions in 3+1 dimensions. And well, non-locality is something we typically associate with high energies or small distance scales, but it's not really a Lorentz invariant statement, of course, because a small ball in Lorentz Lorentzian manifold is hard to define, right? So it's more of a hyperbola. So this will come back, and this is at heart really of all the problems of non-local theories in space-time, and we will get back to that during this talk. But today I want to study a very simple model. So I want to study a classical linear scalar infinite derivative theory on flat space-time in these Cartesian coordinates t and x. And this is how this equation looks like. F of L squared box phi equal to sigma, where let's ask you, can you see my mouse? Is this visible to you? Okay, great. So of course, F is the form factor that we heard so much about the last couple of days. And then L is what we call the scale of non-locality, which sets the scale where effects of non-locality typically kick in and are relevant. Box in my notation is just the wave operator, or the D'Alembertian operator here in the signature minus plus. And this object here is the Laplace operator, which is just the sum of second derivatives, or in case of spherical symmetry, just radial derivatives as usual. And then on the right-hand side, we have an external source. And this is the equation I will be talking about for the first part of this talk. And you see this in linearized gravity equations when you put in an ansatz for a metric. You see this for Maxwell equations and in many other scenarios. So even though it looks very, very simple, it actually covers a lot of different cases. And I think it's a nice a toy model to have a look at. So here's the equation. And before I go any further, there are some important requirements that we impose on this form factor f. So first of all, if we view this form factor as a function of a complex coordinate z, then we assume that it's not zero, meaning that we can invert it everywhere, meaning we can do 1 over f, not the functional inverse, but just the 1 over f, we can calculate this. Also it means if it's never zero, it means that there can be no new zero modes of an equation, of a differential equation, which corresponds to the classical version of this ghost-free criterion. And that's an important difference to higher derivative models, where typically this is not true. Now, also f of 0 is equal to 1. This is another requirement, and we will see that this guarantees the correct far distance asymptotics or infrared properties, and also the correct local limit when the scale of non-locality goes to 0, because you see if L goes to 0, it's just f of 0, formally speaking, and then just the effect of non-locality just goes away. It also has an interesting side effect, which is that it removes non-local effects on on-shell quantities, meaning if you have an object that satisfies a homogeneous wave equation, say box x equal to 0, and you have f acting on this, it becomes f of 0, and then it just vanishes. So this interplays a little bit with what Astrid Eichhorn was emphasizing, that the presence of matter, of course, is very important. So vacuum equations in these non-local theories, they're trivial, right? Because right-hand side is 0, f just goes away, and you have no effect of non-locality. So the presence of matter is very important in this kind of line of investigation. But how do we find a solution of this equation? And so I said already, I will be talking about the green function approach. So we can define a green function g when being acted upon with this differential operator to be this product here of delta distributions in time and space. And then, of course, the field can be written in this particular way here as a convolution of the green function with the source. Notice that I said how to find a solution of this equation, not how to find all solutions or the unique solution. So I will not be talking about uniqueness of solutions or the initial value problem, but instead I will focus on the causal properties of this green function, of this non-local infinite derivative green function, and I hope we can learn something from that as well. So to study these causal properties, it's useful to use the Fourier transform, because we're in flat Minkowski spacetime, so we can do a Fourier transform in all directions. And this is just my conventions for the Fourier transform. And you notice that there's this quantity I here, which is just, of course, the inverse of the differential operator. But we can write this artificially, maybe as a difference or a sum of two pieces here. So there's this purple part, which is the non-local modification, and there is the green part, which is the local part. Now, the local part has to be regularized because, well, it has poles. And so we do this with the usual I epsilon prescription, and that gives rise to the causal properties. But of course, the non-local effects are all encapsulated by this purple term, right? And so this purple term has the property that, there are actually no poles, because recall that we can always calculate 1 over f. That was a requirement that we had. And also, if there is it looks like there should be a pole, right, because of omega squared minus k squared, but recall that f of 0 is 1, so this cancels as well. So this purple term here has no poles in the complex plane. It might have some interesting behavior far away related to entire functions, but there are no poles. So in some sense, if this integral converges in the complex plane, you can just, in the omega k space, in the real space, you can just do a typical hyperbolic integral over these things and just calculate what it is. So we can write the green function as the local green function g and a modification term delta g. And this g here in our case is just the standard two-dimensional retarded expression, which is just the two-dimensional delta function of the space-time distance multiplied by the step function, because it's a causal function. So this function, the local retarded green function, is non-trivial only on the future light cone, which is what we know. But what about delta g, which is the purple part which encapsulates the non-locality? So it's possible to evaluate this analytically in a couple of cases in space-time. I should mention that in this case, of course, we have to specify a concrete form factor. In this case, we specified e to the box squared. If you take e to the box, you find that you can't actually do the Fourier transform. It just doesn't exist because it doesn't converge in the frequency direction or in the momentum direction, depending on how you define your signature and your signs. But in this case, e to the box squared, it exists and it can be calculated, and it takes this specific form here. Okay, what does that mean? A G2003 is a Meyer G function. That's just a special function. But for small and large arguments, we can write down these asymptotics here. And formulas like this have been derived by Luca and Anupam and collaborators in the really nice review article in Nuclear Physics B. Here's the archive number right here. I also have some of these formulas in my PhD thesis and also recently with Ivan in this paper here. So what do these asymptotics mean? Recall that S squared is the space-time distance, and it depends on the modulus of this. And if this is a very small number, we have a logarithmic divergence. And if it's very large, it's exponentially suppressed. So let's start with the second part, the exponential suppression. One example for S squared going to infinity is if t prime minus t goes to minus infinity, meaning that the effect is preceding the cause infinitely long for an infinite duration, and we keep x prime and x constant. And in this case, delta G goes to 0 exponentially, and the green function coincides with the local green function. And this is what Bryce DeWitt calls asymptotic causality. So this class of green function and these theories have some causal properties in the limit when the points are very far separated, either in the purely space-like or in the purely time-like direction. And if you think about the initial value problem, you can maybe intuitively expect that that a Cauchy surface now has sort of like a finite thickness, or a penetration depth that is proportional to this length L here. So it's maybe one intuitive way to think about this, even though this is not rigorous at all. There's also logarithmic divergence in the coincidence limit or for null separation, because you have this log of 0 here. Now, one example where we actually studied this is we studied together with Ivan Kolar, we studied the retarded field of a uniformly accelerated source in 3+1 dimensions. And this is how this equation looks like. So you just have this charge here of this point particle on this hyperbola. We want to know what is the retarded scalar field that is caused by this type of source. And here's the numerical result that we could derive. And let me just blow this up a little bit bigger for you. So what you see here is in the right Rindler wedge where the particle is located at this dashed line here. This dashed line is the local potential that you find in local theory. And of course, it diverges at the location of the particle as 1 over zeta here, which is this distance coordinate. But in the non-local theory, which is this blue line, we see that it's completely finite at this location. So that's good. So non-locality removes this type of singularity in this linearized theory. But there's also something funny going on at the horizon, and I don't have enough time to talk about this properly. But this is due to this logarithmic divergence. But there's prescriptions that we can remove this divergence as well. All right, so this is all I want to say about space-time, and I want to talk about space, which is a further simplification. So now we have not just a simple model, but even a simpler model, because we have a classical linear scalar static infinite derivative theory on flat space. So this corresponds to these Euclidean methods that were presented as well. And of course, now there's no time dependence anymore, and the operator is no longer hyperbolic, but it's an elliptical operator. And how do we find a solution of this equation? Well, we can just define green function in a similar sense as before. But again, I will not discuss here the boundary value problem. But instead, I just want to focus on the properties of this non-local spatial green function. So first off, that's kind of like the main point of my talk is regularity of this non-local spatial green function. So in 3 dimensions, you can write it down in this particular simple way here. And I think we saw an expression like this in a couple of talks yesterday as well. And you see that in the coincidence limit, when x prime approaches x, you see that there's just a sine x by x. So this cancels out and you just have this parametric integral here. It depends on L, but nothing else. And then you're going to go to next to leading order and you find a quadratic term. Of course, it's not clear if this term here converges because it depends on the form factor f. And so you see, in particular, it depends on the behavior of the form factor at infinitely large k, which means that the regularity of the green function in the coincidence limit is dictated by the large momentum properties of the form factor, which is what you would expect. And fields of course, delta constant excuse me, fields of delta concentrated sources, of course, are proportional to the green functions. So the regularity of this green function here already implies that the field of point particles, branes, these kind of things, they're automatically regular as well. Now, the next leading order is a distance squared, and there's a constant C2 that depends on F as well, on the form factor, and C2 in general is positive, which means that there's a minus sign here. And that means that the geometry at the origin is positive curvature, or some people call this De Sitter like geometry. And maybe Valerie will comment on this in his talk on regular black holes, because it's a fairly generic thing that happens. And I should also mention that this happens in many higher derivative theories as well, because you just need that f goes to 0 sufficiently fast as k goes to infinity, and f of 0 is 1. And so this is not a property that's generic just to non-local theories. So we talked about regularity. Now we can talk about asymptotics. And for that, it's useful to reshuffle the coordinates in some way. So we have this integral here instead, but just redefining the momentum integration variable. And if we consider the asymptotic limit when x prime to x goes to infinity, or more accurately, if this dimensionless quantity here goes to infinity, what we find is this kind of expression here. And all we see is, of course, if that thing goes to infinity, then this argument here goes to 0, so f of 0, but we demand that f of 0 is 1. So we just have this integral here, sine x by x or sine k by over k, it's just pi half, and that gives us the local green function. So we see the condition f0 of 1 guarantees the correct far distance or infrared behavior. Specifically here, that's just exactly how you prove this. And this also guarantees that the fields of concentrated sources when you go far away or when you turn off non-locality, right? This limit here at finite distance also corresponds to setting L to 0. It immediately guarantees that you recover the results from the local theory. And again, this is not just particular to these non-local theories. It also happens in higher derivative theories as well. Now, one thing that's a little bit more technical that I wanted to mention is inspired by Irina's talk on heat kernel representation. So we can do something similar for any form factor f here. And we can write this green function in d dimensions, these spatial dimensions, as this sort of like double Fourier transform of this heat kernel in imaginary time, which looks like this, where tau plays the role of an imaginary time, and it satisfies this heat type equation. Now, regularity properties are difficult to prove from this representation, but it does work for a wide class, if not all non-local form factors. But not just, that's the more important part, it doesn't just work for exponential of Box or Laplace operator, but also for more general theories. And we use this when you're constructing regular Girardon solutions, which is basically when you take a point particle or a pencil and you boost it along its symmetry axis and rescale its mass so that the limit is finite when it goes through the speed of light. And that limit, this representation here is extremely useful. And it's not clear if this works in space-time as well, because of course the heat equation is very different for a hyperbolic operator. So we don't really know. Nevertheless, this is a very useful representation for certain applications. But speaking of applications, one thing I wanted to mention explicitly here is the field of a cosmic string, because cosmic strings are well known. They have interesting properties. They're locally flat, but not globally flat. They have a curvature singularity here along the z-axis, which will be the x that goes up and down on your screen, the symmetry axis of this geometry. And here, of course, this is a plot of the transverse spatial geometry, two-dimensional geometry, with the famous angle deficit here written, seen down here, and the conical geometry. Now, in the non-local theory, what happens is you get this kind of geometry. So it's the smoothed out cone at the bottom, which is asymptotically flat, not locally flat, asymptotically flat. And the curvature is smeared out along the z-axis. So you see, for example, here is obviously positively curved, right? And the angle deficit becomes a function of radius, and then only when you're far away approaches this asymptotic constant value that is just given by the string tension. And you see something happens when you go from here to here, and of course something becomes more smooth. And so that's why I wanted to mention smearing functions and integral kernels. So you see here that we define this object k of x minus y as the inverse of f acting on the delta function. So this is just a definition of this object, and this is a concrete representation that you can find. And you see, maybe you remember, it looks almost exactly like the green function, but there's a factor of k, not 1 over k, but that's the only difference. So what's the interpretation? Of course, if you look at the linear equation, and here I'm actually putting a source on the right-hand side. So this could be a Laplace type equation. What you actually find is that if you put this inverse on the other side, then this corresponds to Laplace phi is equal to something. But that something is, well, it plays the role of an effective source, right? So this is the right-hand side of the Laplace equation. And so you can just identify K as sort of like an effective energy density or mass density. And effective in the sense that it's generated by this non-locality. And in these linear theories, of course, you can always just put it on the other side and have that one-to-one correspondence. But we know that K has to be what mathematicians call a nascent delta distribution, or what physicists call a smear delta function that follows immediately from the definition here, right? Because f of 0, if L goes to 0, then it's just 1 over f of 0, which is 1. So as L tends to 0, K has to become the delta function. That's already clear in this definition, but we can verify this explicitly in a simple case when we just have e to the box or e to the Laplace here in this case. And we can calculate what is this object, and it's just a Gaussian with the standard deviation of at the scale of non-locality L. And of course, we all know that if L goes to 0, then this becomes the delta function again. So that's, I think, is a useful way to think about this. But these integral kernels, they also have some surprises or maybe some unexpected features. And here we plot these effective densities over dimensionless distance R divided by L on a logarithmic scale. And we plot here the absolute value of the effective energy density rho effective of R being the distance. And we plot this for different theories. So the blue line is the one that I showed you before. That's just the Gaussian that is just strongly decreasing. But if you take theories like e to the Laplace squared, which is this green line here, or e to the Laplace cubed, which is this dashed orange line, you see that there are some sort of periodic oscillations in these distances. And they're very hard to see because they're logarithmically, exponentially suppressed. On this logarithmic diagram, you see this. And I should say, because we plot here the absolute value, whenever the slope goes to minus infinity and goes to plus infinity, there is a sign change. So the energy density doesn't keep the same sign. It flips signs for all these oscillations. And that's, of course, very unusual. And it reminded me of these Friedel type oscillations that you find in condensed matter systems when you put an electron in a cold metal and you look at the resulting field around this, you get these characteristic ripples to negative and positive energy charge densities around the electron. And it just kind of like reminded me of this. And it's kind of interesting, I think, that this happens, and I don't really know why. This happens in other models too. So just for fun, I looked at this model that Frank Sauer-Essig was proposing the other day, and in the spatial setting, of course, which was this 1 over k squared 1 plus k squared tanh type model. But I couldn't integrate this. So I just approximated tanh of k squared as k squared by 1 plus k squared, which is reasonably good approximation. And that corresponds to this kind of form factor here. The important part is that this is an infinite derivative form factor because it has a 1 over 1 plus k squared. So you have to, if you want to know what this is, you have to do the series expansion of this thing. So you see this satisfies all our properties. F of 0 is 1. And f at infinity grows like k to the 4, or actually k to the square. But it still means that these integrals before are finite. So this is one reasonable non-local form factor. And you can calculate the corresponding static green function, which has this funny looking form here, which is the 1 over 4 pi r is just the local part. But then you have these cosine and sine terms that are exponentially suppressed. And you see that this is oscillatory. But you also see that at the origin, you see that it's the 3 minus 3. So this is perfectly regular at the origin. So it's a regular theory. But it also has these oscillations. If you were to apply the box operator to this object here, you would find this effective energy density. And of course, because of these oscillatory terms here, you actually find this oscillatory behavior as well. All right. So with this, I want to conclude my talk. So what have I shown? I think I hope I have convinced you that we can construct a wide class of these regular solutions in non-local linear problems. And hopefully we have generated some sort of non-local intuition with these kind of studies. But I also want to mention what I have not shown, which is that you can apply similar methods in a partial Fourier transform situation. So you can have, for example, a purely time-dependent potential, or purely space-dependent potential, and perform Fourier transform just in the other transverse conjugate Fourier momentum. And we have used these methods, for example, in particle creation and particle scattering in quantum mechanics, where we can actually define asymptotic locality, or we can use this asymptotic causality that DeWitt required, and define reasonable in and out states. And there are some papers where we did this, and one that came out just a couple of months ago. And what could be next? Well, there could be exact solutions in nonlinear classical gravity, but in the non-local case, this is very difficult, but perhaps is possible and certainly interesting to look at. And another way would be to just explore perturbation theory using these green functions, using sort of like the Lippmann-Schwinger type equations. So as an afterthought, I wanted to mention a quote that supposedly goes back to Einstein, which is the horizon of many people is a circle with a radius of 0. They call this their point of view. And it's a nice geometric little statement. That's my time. I'm almost done. I think that the mathematical methods that I presented in this talk are sufficient to prove theoretically that non-locality has the potential to broaden our point of view like this. And I like to think that this conference is an experimental verification of that theoretical claim. So I would like to thank again Luca and Sravan for their kind invitation. Let me speak here to all of you. I would like to thank Valerie, Andre, Jose, and Ivan for their collaboration. And I want to thank everybody for your attention. Thank you so much.
Okay, thank you very much for this very interesting talk, and also for being very precise with time. And there are many questions. I think Alex was the first one to raise the hand. So if you're there, you can talk.
Yes, thank you very much. So first of all, thanks for this nice talk. Indeed, a lot of non-local intuition. And I have a question about the first part where you tackle the Minkowski problem. If I understood correctly, you try to tackle it in Minkowski signature in 4 dimensions. Is it correct?
Yes.
I'm not missing something. Then I kind of disagree with your conclusion. Okay. And my disagreement is very simple. I did the same computation, and what you write with respect to this Mayer function is correct. But the problem is that you must have observed divergence of the integration during integration when you do angular part of your integral, because anyway, you go to some spherical coordinates or whatever, you don't do it very straightforwardly. So yes, when you go to spherical coordinates, you will have angular singularity. And actually the trick, which also came to me as a mistake, is the fact that this Mayer's function defined in some textbooks is defined correctly, but it doesn't cover all the region of integration from 0 to infinity, which you must cover. And as such, practically speaking, your answer, the Mayer function, is correct, but in a very, very narrow domain of your manifold. Definitely not for the whole space-time. It's correct, but on the rest, and let's say the domain where this answer is valid is very, very narrow. It's some domain which you can find in Grashstein-Rizek book, for example. I did the same kind of trick. And finally, you find out that defining this on the whole manifold, on the whole infinite space-time, kind of messy point. This is exactly where absence of Wick rotation arises. This is exactly this is exactly where you hit all the problems. So I kind of want to say that this result, which we see now, is just incomplete, and maybe it cannot be done complete in Minkowski signature because integral is divergent.
Well, I mean, you have to regularize these integrals, right? But I just want to, I mean, this is an obvious statement, but if you want to arrive, for example, at this local result, which is this delta function, of course, this integral is also not well defined, right? So you have to regularize these integrals, and if you want to see exactly how we regularize these integrals, you're completely correct that there is some regularization involved. And then I can point you to this paper with Ivan and myself, where we spell this out in detail in the appendix. But I'd be happy to look at the references you mentioned just to make sure that we're talking about the same thing here.
No, so you see, you are speaking about regularizations, which are kind of about poles or whatever. I'm telling you about singularity, which arises from essential singularity at infinity, which is much harder to avoid. You can try to do something, but this is other game. But anyways, I believe we can discuss in the discussion.
Yeah. This is a more technical point, but it's certainly interesting. Thank you for bringing it up.
Okay. Yes, so maybe it's better to continue the discussion. Now, if there is a very, very fast question, I see that there are many hands raised. So Ravan, I think,
Yeah.
was the first one to raise.
Yeah, I'm wondering. Yesterday, it's also related to yesterday's talk. Barwinski said, like, you can, for example, if you violate Lorentz invariance and, for example, put non-locality only in the spatial sector. So, do you get regularization? And another thing, short comment. Maybe if it is a solution for the comment Alexis said. So, for the question Alexis asked.
Yes, so one of my collaborators here at William and Mary, actually, Chris Carone, he's working on these Lorentz violating non-local theories, and certainly that solves this type of problem, because then this divergent mode in the omega direction just vanishes. So this can be done. I'm not sure if it can always be done, but there are certainly cases where it can be done. Of course, it imposes a very strict constraints on the scale of non-locality, because then you have all these Lorentz violation bounds by Kosteletsky and other people like this. So you have to make sure that it's somehow compatible, because Lorentz violation is strongly constrained, of course. So that might get you in different kinds of troubles. Yeah, but it certainly it can simplify some aspects of it. Yeah.
Thanks.
So we should probably postpone the other question to the discussion session. And so let's thank again the speaker.